Okay, welcome to the lecture number 21. And so the last part we did Laplacian PDEs. Now we're going to start on a new part, hyperbolic PDEs. We're also going to talk about the exam. And then for Friday it will be wave equations and some other things. There's another quiz on the 14th, and this project is still kind of tentative. I don't know about that. It may be too much to do, so we may extend that a little bit further back. So we'll see what happens. And then, of course, looking a little about a month in the future, the exam number 3 is on the 2nd of April. So this is a new part. So the Farlow, essentially we need to look at chapters 16 through 19. And that corresponds to the yellow book, Salsa's book, chapter 5. If you're interested in what we're doing and you want some more references, there's Physics of Waves. That's this one. It's pretty good. It's fairly cheap, maybe $15 or $16 at Amazon. But it's not required. That's just if you have a lot of interest in it or something that you're doing in your research. Okay, and if you're interested in the acoustics part, which is also a wave equation, then you can find some textbook somewhere. There's one that I suggest, but again, it's an optional book. You don't have to have it for this class. And in case you're wondering, that $ means it's pretty expensive. We'll talk about some of this later, so I'm just going to skip that. And let's pretty much immediately go and look at the exam. Okay. And this is for the online students. And again, this is a warning. If you have not completed the exam and sent it in, then this is not what you should be watching. So that would be a serious case of dishonesty. Okay, so we're just going to go through this. First thing is my name, think, and then plan and write. Well, let's just go through. Okay, solution to a boundary value problem depends on two things. Number 1, governing equation. Number 2, boundary conditions. They just shouldn't watch it. Yeah, so we had a question from the... No, that's okay. We had a question from the producer, and whether we should pause it, but we're just going to keep going. And again, if you're an online student and you haven't taken the exam, you should not be watching this. So, governing equation and boundary conditions. That's all. No initial conditions. A lot of you guys put initial conditions for something that matters. It doesn't matter. Those initial conditions don't matter because there's no time derivative. Value of, okay, so let's just draw this. So we've got this sort of a situation, and I said that I've got a value here, and it's equal to 1. What's the maximum possible on the boundary? Well, I'll just give you a theorem. You could probably figure it out. The maximum value on any sort of Laplacian domain like this always occurs on the boundary. And you can go through and derive it and show it for yourself. So if you have a value inside of x, then you're guaranteed that it's going to be between the minimum and maximum of the boundary. So if the minimum is 1 and it's on the interior, that means it's 1 everywhere. So the value, we can say this. And if you want to use that Poisson integral formula or any of the other formulas that we talked about, you can show it very quickly. So it's pretty simple. Green's function on the square domain. Some of you considered that as find the Green's function on the square domain. That would be hard. That's not what this says. It says it's given a Green's function, not show or find or derive. So we have some domain here, And we have a g, so that's going to satisfy what? Green's function is going to satisfy the governing equation and boundary conditions, right? Okay. So what is u of x and y is going to be this, right? So we can do that. So the solution is the integral over the domain of the Green's function and some input function. Well, we've got an input function here. So if we just substitute, well, let's look at it right quick. That's a delta function, delta of x minus 0.5. That means that the only value this has is at x equals 0.5, so 1/2, and it's equal to, what's sine of pi 1/2? What would that be? Sine looks like that. That's pi. This is pi over 2. So it's equal to 1. So it's equal to 1 along that spot. So we can simplify this. It only has a value there, so that means that let's call that the x direction, right? So that is going to be only has a value of 0.5. This is 1, so we can drop out one of these terms and get, let's see, x, y, 0.5 eta. Is that right? Let's see, we're going to be integrating over eta, and then that's a 1. And the only one that matters is that, so the eta is a d eta. So that should be what you get. Of course, if you got to this part, that's worth something. This is, I basically gave partial credit depending on how far you got. So that's what that one is. Okay, finite difference approximation. We can say that del squared u is equal to, what would that be? It's approximately equal to north plus south plus east plus west. Nah, that's terrible. Minus 4 times the center divided by delta x. I said delta x and delta y are equal, so we can just use delta x. Some of you actually came in and solved for UC. That's fine. I didn't have a problem with that. Okay, and then it said draw a stencil. Well, if we have an x direction and a y direction, we have a center value, an east, a west, a north, and a south, and those are equal to 1s, and those are equal to minus 4s. So that's it. Potential function and stream function for a vortex. Okay, well, let's sketch. We know that a vortex, the streamlines are basically going to be circles. And we also know that the potential lines are basically going to be orthogonal to that. So basically we're going to have that. So we can back out of that. We're going to have a potential function that's basically equal to something times theta. So constant values are going to be constant thetas. And there's going to be some constant term. And if you didn't quite get the constant term, so what? It doesn't really matter to me. But it's 1 over 2 pi. That's the canonical form. Stream function, well, it's going to be depending on radius, and it happens to be a log of radius. So again, it's going to have this arbitrary constant term, and a log of radius. So if you had something similar to that, that's fine. Okay, the next question, number 2. This was almost a giveaway question. This was one I was thinking was going to be the easy one. Let's see, what do we have here? We have some domain, radius of big R. We have a R and theta. And I want to find the solution at the center. Okay? Well, I did it several different ways in my solutions. In fact, 4 different ways. So let's just go through those and look at them. Method number 1, we could use that Poisson integral formula. That would be fairly quick. All you have to remember, if you didn't quite get this, you don't remember that, that's fine. All you have to remember is R squared minus R squared, big R squared minus little r squared. That goes to R squared divided by something which is R squared, so that would be 1. So basically it's saying at the center, we just take the average of the boundary. Well, what's the average of the boundary? Well, this guy, this term, is the one that almost everybody had problems with. It's just a line. It starts at minus what? Let's start at wherever it starts. It doesn't matter. It's symmetric. The integral is 0. I could make it whatever. I could make it 10 million times theta minus pi. It doesn't matter. It's the integral from 0 to 2 pi is 0. There's no contribution from that. What about the other terms, the sine terms? Well, those are all harmonic. They go to 0 too. The average over the boundary is 0, which means the value at the center is 0. Okay. What about a method number 2? Instead of doing that Poisson integral formula, let's just plug in our equation that basically the sine and cosine terms. Well, we have a r over big R to the n power a to the n cosine of n theta plus bn sine of n theta. Well, r over r to the n is, in this case, 0 over r to the n. And for any n that's greater than 0, that's going to be equal to 0. However, when n is equal to 0, it's equal to 1. So the only coefficient that we really need to worry about is when n is equal to 0. Well, there's no b0 term. Sine of 0 is always 0, so that's useless, right? Cosine of 0 is 1. So it's saying the value at the center is equal to the a0 term. And what's the static offset in this problem? We established before that there's no static offset. The average of the boundary is 0 again. So you could say it's 0. Or, if you wanted to do method 3, the theorem, the value at the center of is the average of the boundary values. You probably could have found that in Salsa. I don't know if Farlow said it or not, but that's the by inspection, almost trivial way to do it. Average is 0, value is 0. What if you wanted to do it the hard way? And remember, in the run-up to this exam, I told you guys that you need to either, there's going to be a problem that either takes a couple of lines or it's going to like two pages. This is the 2-page solution. If you wanted to do it the hard way, and please don't do it this way, you can find the expansion to this. Well, these terms are pretty simple. The sines, that's almost trivial. What about this? That one's not going to be so trivial. It's going to have an infinite sine series or an infinite cosine series. So you can do that. For a0s, well, a0 is 0. You can do that for the an's, and you get some zeros. You can do it for the bn's, and you can keep going, and it's more work. And more work. What is that? Two integration by parts, and you end up with a recurrence formula for the bn's. And a general solution is that which we saw before, and so we plug in these bn terms. The only one that really matters, because r over 2 to the n is going to be 0, except when it's except when n is equal to 0. Well, the B0 term is 0, so it doesn't matter. So solution there is that just average of the boundary condition equals to 0. So U is equal to 0. Okay, number 3. This one is kind of a spin-off of a quiz that we had. Remember, we had a quiz, and I had a derivative term in there, and we changed it to a Dirichlet type boundary condition instead of a Neumann type boundary condition. Well, this one is just continuing with the quiz, and just to see if you can take a solution and then modify it just a little bit to get a different type, or a different type of boundary condition. So if we solved there, let's just solve that. What would that be? That is U is an a to the n, what is that? A to the n, r to the n, and then, well, that's a b to the n, a sine. Something like that? Is that right? Let's make sure that's right. We've got a domain here. R is equal to 1. Okay. So we can just read off the terms. The term is 1. So that would be, well, that's 3. So the n equals 3 term is 1. So that's sine of 3 theta. So that's the solution here. So can we modify that? Well, let's just modify it by saying that kind of would, maybe there's a solution that looks like this that fits the Neumann boundary condition. So basically we need to take the derivative of that and fit the boundary conditions. Well, the derivative of that is 3a r squared sine of 3 theta. And that's equal to sine 3 theta. So what is a? Well, we have a 3a equals, what did I do? Oh, that's on the boundary. So on the boundary, r is equal to 1. So 3a equals 1, a equals 1/3. So what? Solution is 1/3 sine 3. Is that correct? Almost. One student in this class outsmarted me because I said, that's the solution. That is not the solution. That is a solution. So what we forgot here is that this is a derivative. There is no boundary value, so we could add a constant here. If you add a constant to that and you take the derivative, does it still fit the boundary condition? Yep, it does. So if you did this, you got full credit, because I did it that way and I messed up. If you did that, then you got extra credit because you outsmarted me. So yes, does a solution exist? Yes, it does. We can actually check that. The flux, basically what you do is you just integrate the flux. Integrate the flux over the boundary, and you're going to get 0. So a solution exists. It has a solution. It has a lot of solutions. There is one solution. There's all the solutions. So that's the answer there. Okay, so next one. This one was the spherical ball, had a radius of 1, boundary condition, determine the temperature inside the ball. Okay, this is another one where there was an easy way to do it, and there's a really, really hard way to do it. what does this kind of looks like a, we've got that. All right, and we've got some radius, and we've got some, if we look at the angle here, we've got a 5. Okay. What's the general solution? General solution is u of r. Theta phi is, let's just call it an a to the n, r to the n, p to the n of cosine phi. Okay. So we're looking to fit this boundary condition to that. So we know what these p to n's are. That's what I gave you. So what should we do here? We want to write this boundary condition in terms of pn's. So cosine squared of phi plus cosine equals, well, if we look here, we're only going to have cosine squared, so we're only going to have up to p2. But we could have p2, p1, and p0. So let's just say, I don't know, let's just call it A. A p0 plus B p1 plus C p2. Well, we can expand that. That's going to be equal to, right-hand side is A times 1 plus B times cosine plus C times this, which is C over 2 times 3 cosine squared minus C over 2. Okay, and so that has to be equal to cosine plus cosine. So we just need to match terms. Cosine squared, there's a cosine squared. So term in front of there is 1 equals 3 halves C. So C is 2/3. Next one, we have a cosine, so 1 equals B. So B, well, that's, okay. What's the next one? We don't have any constant terms. Yeah, we have some constant terms over here. So we have 0 equals A minus C over 2. And that means that A is equal to C over 2, which is 2/3. That's 1/2 equals 1/3. Okay. Oh, I'm sorry. You guys couldn't see what I was writing. Could you zoom out? Okay. So, using that, we have basically found what these A terms are, right? So we could just write the solution down quickly here. That would be, start with the A, that's the P0 term. So it would be 1/3 R to the 0. This is a 0 term, A0 term, right? Goes to A0, or A goes to P0. So P0 is, we'll go look at the, P0 is 1. Plus a B, well, B is 1, times P1. Well, P1 up here is cosine. And what's next? C. C is 2/3. That's P2. Come up here and look for P2, and we have that. So 2/3 of 1/2, 3 cosine squared minus 1. Okay. Now you could reduce that a little bit further, reduce whatever you want to do, but that's basically the solution. Oh, whoops, I made a mistake, didn't I? That's correct. That is correct. This is R first power. This is R to the second power. Okay. So that is Everybody agree with that? That's the solution now? Okay, so that's essentially it. That's the exam. The average was 73. High was 94. Do we have any questions about that? You guys used pretty much the entire time to take it. So that's a good clue to me that maybe I don't know exactly what, maybe that clue is not so much, because a lot of you really spent a lot of time on this question, because I don't think you knew how to deal with that. I'd say probably half the class came in here and said that we're doing a sign expansion. So AN sine or BN sine of N theta. And you came in here and you said that what did you say? B0 equals theta minus pi. So then you said that meant that the solution was U of R theta was equal to, at 0, that the center solution was equal to theta minus pi. That's not going to get you very many points. And the reason why is, number one, it's incorrect to even say that you can't directly take that term and say that that's equal to the coefficient. That's incorrect. Second problem is that at 0, the value depends on theta. So now we're going to have this, let's zoom in on the center point. So kind of do a 3D curve, 3D graph. So here, as we're going around theta, so we have the solution value U, we have basically an X and a Y, so that's an R and theta. So we're going to go around in the plane, and you're saying that the value depends on the angle. So we're going to have it's going to sweep up, and then we get to 2 pi, and it's going to chop down. It's going to have an immediate discontinuity between at some point, right? That you can't have that. That doesn't fit the Laplacian. Laplacian is always smooth. So if you put that as a solution, it's very, very badly wrong. Are there any other comments or questions about the exam? Would you like the exams back? I can do that. Oops, that's not mine. That's not yours. There. Okay. If you have any questions about how it was graded, you can come see me. I do need to warn you that I'm in the middle of another project now, so my time is going to be fairly limited, and I'm going to be a little bit stricter on the office hours just because I have some significant things to get done. Okay, we have a few minutes. Actually, we completed that exam in what? 20-some minutes, 25 minutes? Okay. I had new notes somewhere. Yes. Let's go back and look at a little bit of a review of lesson 15, where we're talking about convection and diffusion. And remember we said that convection is the transport of some U value because of the movement of a substance. So it's like you're outside in the wind, and there's a leaf that falls down. Well, the leaf is convecting with the air. It's flowing with the air. The flux due to convection is the velocity times the value. So velocity times the state. And here, this is the mean free. That's basically the velocity of the air. And this is the state. So you may be saying, well, what happens if the state is the velocity of air? Well, we'll talk about that later. But right now, we're going to go with linear convection. So there's our governing equation. It basically turns out that you can take the derivative of the flux with respect to x, and this is your governing equation. And remember, we also said that there was a flux due to diffusion. The flux due to diffusion is some value d times the derivative of u, so that gave a governing equation of du dt is equal d, which is a constant, u sub x sub x. So remember again that our transport equation is a pretty good one to remember. It's du dt plus df dx. So it's change in state with time plus change in flux with space is equal to 0. So let's just solve a convection type problem. This would be Farlow's, what is that, on page 113 and 114. So essentially we have du dt is equal to minus v du dx. So it's a pure convection type problem with 0 initial conditions, and then at some time, at time 0, we essentially start having some value p at x equals 0. So you could think of this as like, I think in the Farlow book he talks about it being a river, and at some time 0 we start adding some pollution or something like that. This could be pretty much anything that has convection in it. So we just are adding some substance at that location at that time. So we're going to look at it. There's a little hint of something called a solution by characteristics. If we took our governing equation and we kind of rearranged it and used a chain rule, and then instead of saying du dx, we said du, or we changed that into a flux, that's what this term is, minus vu, that's the convective flux. So that would be df du times du dx. So we've used the chain rule there. And then we can kind of rearrange stuff, and we see that if we cross out these u terms, we have dx dt is equal to df du, which means that there's some particle moving along. We can find a constant line that particle a constant curve that particle is on as a derivative of the flux with respect to the state. That's what this term says. But we'll get into that later. So that's just kind of a hint of what we might do later. But we can solve it right now with the Laplace transform. So let's just take the Laplace transform of the time derivative and the Laplace transform of the space derivative, the diffusion part of it, not the convection part of it. So Laplace transform of u sub t is s of u minus u0. Well, u0, we said that the initial state was 0, so that's 0. Minus, or equals a minus v du dx. Well, that's the Laplace transform of a spatial derivative. We can also find the Laplace transform of the initial condition, which is just p at that point. So that's p over s. So the solution to U is P over S e to the minus Sx over V. See how we got that? There's the V term. Just a solution to that. We can check that that's true. So now, if you go look in the back of your book, I don't know if I brought my book. I did. We are looking for inverse of that. So we're looking for some function that if we take the Laplace transform, we get this. Okay. Right there it is. E to the minus as over s says that that is a Heaviside step function, t minus a. Well, our a is this x over v. So our Heaviside step function would be p, that's just a constant, Heaviside of t minus x over v. So visually, here's the solution. Now make sure you recognize that this is in the xt plane. So we have time, as time advances, it's going this way. This is x direction. So you start putting some pollution or put some object or something in that water at this time, and as time goes on, it's going to convect downstream. That's almost, you can get that from intuition. The velocity of which it advects or convects is v. So we can use a Laplace transform to solve that, or what we could do, let's change the variables just a little bit. So basically, instead of sitting at one point and looking at what happens, let's move with the flow. So let's change to a new variable called zeta is equal to x minus vt. Well, that's interesting. You put that into here, what are you going to get? Substitute into the solution that we just found, the Heaviside function, so x is equal to zeta plus vt, substitute that in, and we get h of zeta. That means in a Lagrangian coordinate system where you're moving with the flow, on one side you have solution state of 0, on the other side you have solution state of p. So there's some really nice characteristics, well, really nice properties that come out of this, and one of them is that you can track the characteristic lines and solve on one side and on the other side, and we know that the value has some relation as it goes along that line. So we could end up solving something like this, and I think we did this in a previous class. I had somebody come up here and try to solve this. So if I gave you a particular solution for initial condition and said, there's the governing equation, how does it behave? Well, it just means that that wave is just going to move downstream. Now, what if we went into the zeta coordinate? What does it look like? If you're moving with the flow, then you're not going to see any difference. If you're at this point, value equals 1, it's just going to track value equals 1. If you're at that point where the value equals 0, it's going to track value equals 0. Okay, I just wanted to go and review that just a little bit because that's going to be something that comes up in this wave equation portion. So now we're officially going to go into the new part, which is part 3, hyperbolic problems. So this is basically lesson 16 through, I don't remember exactly where it ends, like 20-something, more than that, 30, yeah, 16 through 30. So that's basically what we're going to look at for the rest of the class. So let's start with this. Longitudinal waves in a rod. So if we had a metal rod here, and we have it held, and we hit the side of it, there's going to be a wave that travels in it. Let's derive how that happens. Okay, so we're going to take a little section, a delta x section out of the rod, and look at the forces on it. Well, at any point in time and space, we're going to have some force going left. We're going to have some force plus a df dx delta x on the right. There's going to be some mass associated with this, mass per volume, so a rho. There's going to be some cross-sectional area associated with it, right? So we have some cross-sectional area, S. Okay, so if we just apply Newton's law, it says that sum of the forces is mass times acceleration. And that's good for this little element that we have. So mass times acceleration. Mass. What's the mass of a delta x section? Well, we've got an area times a delta x. That's going to give us a volume. So S times delta x. A rho is how much mass per volume this metal rod has. So mass times acceleration is going to S, rho 0, delta x, d squared v dt squared. So basically what we're saying up here is that we're going to measure any deflection or any deviation from the 0 point at any location with a v. So the acceleration is d squared v dt. That v is not a velocity. That v is a distance. So if we have a stress-strain relationship here, so we can say that, and this is just basically out of your undergrad class in structural dynamics or whatever it is that you did, some materials class. Your stress is related to your strain with Young's modulus. Well, stress is just a force divided by area. So that means our force is S, which is cross-sectional area, Young's modulus, and a derivative of the deflection. So if we combine this and that, we're going to get S rho dx, or S rho delta x, d squared v dt squared equals, well, the summation of these is there's a minus f, and there's a plus f, and a plus f plus df dx delta x. Well, these f's cancel, and so we end up with this term and that term. Well, you can cancel delta x because it really doesn't matter what delta x could. You could have delta x this or that. It doesn't matter, so it means that we can pull it out. And if S is, or the cross-sectional area is constant, and we can divide by rho 0, we end up with d squared v dt squared equals e over rho d squared v dx squared. That's a PDE. In fact, that's called a wave equation. You might recognize it a little bit better. Let's just do a canonical form here. Right? That's kind of what it looks like. So there's the math canonical form. Here's the physics engineering problem. This looks like what we did in that project, didn't it? We had the fourth derivative, didn't we? So we're going to end up with a bunch of waves. It's very similar to what we did in the project. But what's the wave velocity? Well, we're going to kind of cut to the chase and I'm going to tell you that the wave velocity is the square root of this constant. We'll derive it somehow later, or it's in Farlow somewhere. So for a steel bar, and I apologize to you guys that are not using English units and we're interested. Young's modulus is about 30 million psi. Density is about 7 times 10 to the minus 4 slenches per inches cubed. Well, nobody really has any intuition for slenches. That's basically a little less than a third of a pound per cubic inch. Take the square root of those, and since this is English units, we have to be very careful. There's a 32.2 and a 12. Anyways, it turns out to be 17,000 feet per second. If you take a metal rod and you hit the end of it, the wave that goes through there is 17,000 feet per second, 5,000 meters a second. That's fast. Okay, so from the engineering side of it, what could we do with that? If we had a high-speed camera or some way to measure the velocity, or maybe we should have a long bar and we can measure the time difference between when pulses arrive and when they go past certain locations, we can measure Young's modulus with that, right? We can go in here, hit it. It takes a delta t, over some delta L, some length, and some delta T. Go back, solve for what the wave velocity is. It tells you what E is. You can go measure rho on a scale somewhere. See what the dimensions are, divide it by the weight, get rho, find E. So there's a lot of engineering applications to the wave equation. And in fact, I would say that this is where the class becomes more fun, because honestly, the diffusion equation is nice, but it's kind of boring. The Laplacian is a little bit even more because it's a steady state. But wave equations are pretty neat. There's a lot of different things that happen. A lot of different physical properties or physical problems are associated with that. What about a taut string? Taut just means it's tight. We have some force on it. So let's give it a mass per unit length. Let's give it a tension. And then it has some function that it has some shape associated with it. We're going to zoom in on one particular section, and let's just zoom in somewhere around there. This kind of looks like this, right? So we've got a string or a rope. It has some deflection, some curve associated with it. It has a tension on both sides. There's some difference in angle. So on the left-hand side, it's an alpha 1. On the right-hand side, it's an alpha 2. So let's just do a Newton's law. Force equals mass times acceleration. Mass is, we have a lambda naught, which is a mass per unit length, and then a delta x, that gives us a length. And v double dot, that would be basically acceleration. All right. V is our displacement. That's not a velocity. So what are the forces in the v direction on a delta? So do we want v direction? Yes, we do want v direction. The v direction on a delta x section. Well, we have this force here, and we have that force there. So this one is a minus t sine of alpha 1. This one is a plus t sine of alpha 2. Well, that's going to be a nonlinear equation. But if we make an assumption that there's not a lot of deflection, which is going to be mostly true, within a section we're not going to have a lot of deflection, especially for a small delta x section. So we can say that alpha 1 and alpha 2 are pretty small, so sine of alpha 1 is about alpha 1. Also happens to be about equal to tangent of alpha 1. If we say that's true, then we can just say that alpha 1 is basically the derivative dv dx. Okay, so now we have the force is equal to minus t dv1 dx plus a t dv2 dx. Combine all these things together, speed up here plus that. You get here. Well, that's interesting. Look at this. We basically have something on the right minus something on the left. Let's divide by delta x. What's that? That's a finite difference for the first derivative. So we're looking for a derivative of this guy. Derivative d dx of dv dx. So d squared v dx squared. And again, we're going to have this constant. So if I tell you what the tension is and what the density per unit length is of a rope or string, you can tell me what the velocity is, right? What's going to be the velocity? It's not nothing. Square root of t over the mass per unit length. Anybody want to hold the end of a rope? Not be on the end of the rope after the exam, but hold the end of the rope, please. Somebody. I don't care. Just somebody. Maybe it's not a good idea to show up with a rope after an exam, but we'll see. Okay. You want to come a little bit closer this way so the camera can pick us up? So we have a density per unit length, right? We're almost out of time, so we'll just do this pretty quickly. We can pull a tension. You ready to pull a tension on it? Okay. And then, somebody else want to volunteer? You're already up. So I don't know how well it'll show up on online student, you're going to get on the other side so they can see you sort of get in the middle, come to the middle, and get on the other side of the rope. Okay, and pull it tight. Okay, give it a deflection and then just let go. So we're going to have some vibration. So it's kind of hard to see. This rope is actually not very good because it has a lot of diffusion. It's basically, as it moves, it dissipates energy, so it's going to have a little bit of a loss. So it's not going to be a perfect string. And then let's see if we can, actually you can just sit there and know. Okay, I'm going to try to give it, so we're going to get a fundamental solution. So there's one, so like a sine term. Let's see if we can get a second one, something like that. And if we go up, we can even get higher frequencies. And if we didn't have quite so much diffusion in the rope, we'd actually get a standing wave. Unfortunately, this rope tried it last night and I was kind of disappointed too. It doesn't reflect enough back. In other words, it's dissipating energy as it goes along. So this would have both the wave equation and it would have a diffusion equation associated with it as well. But this is basically what we're talking about. We've got some rope, we've got some tension on it, and then somebody's going to do that. And there's a good one. So we can see that there's a velocity associated with that. Let's pull it really tight, so if we can make the velocity higher. See how the velocity of it's higher? Okay. If you guys want to, you can go now, or if you want to experiment with it, you can. We can terminate the recording right here, though. Okay.